Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out another example to draw the shear force and bending moment diagram for a beam. Let us start. Draw the shear force and bending moment diagram for the beam shown in figure. Locate the point of control flexure. The beam is supported at A and C. There are three different loads acting. One is a UDL of intensity 10 kN per meter for 6 meter length, and there is another point load at 3 meter away from the left end, and a UVL uniformly varying load varying from 0 intensity to 30 kN per meter. So it's a triangular load with the maximum intensity 30 kN per meter. It is acting over a length of 2 meters. Now let us find out the support reactions by taking the moment summation with respect to point A. So while taking the moment summation with respect to point A, this UDL, it is acting for 6 meter length, and the resultant of that UDL will be coming at 3 meter away, that is half of 6, 3 meter away, and the resultant UDL will be 10 into 6, 60. 60 will be acting along with this point load. So you can take 60 plus 20, 80 into 3, or separately you can take moment. So I'll take the moment separately. So 10 kilonewton into 6, 60. 60 is the resultant of UDL. It is coming at this location. At B only it's acting the resultant load. So 60 into 3, that will produce a clockwise moment. And 20 also will produce a clockwise moment, 20 into 3. RC will produce an anti-clockwise moment, minus RC into 6. Now the resultant of this triangular load is 30 into 2 divided by 2, that is 30. 30 into 2 divided by 2 is 30. It is the resultant you calculate by area of the triangle. So the resultant load is 30 kilonewton, and it will act at a distance of 2/3 from the 0 intensity side. 2/3 of span. 2/3 of span from the 0 intensity side. That is 2/3 of 2 meter. That is 1.333. So the distance is 1.333. So you can take 30 into the distance from the moment center will be 6 plus 1.333 or 7.333. So 30 into 7.333 is equal to 0. That will be the moment summation. So by taking the moment summation, 10 into 6 into 3 plus 20 into 3 minus RC into 6 plus 30 into 7.333, that is 6 plus 1.333. 7.333 is equal to 0, or RC is equal to 76.67. Now to find out RA, you can subtract this reaction from the total downward load. Total downward load is UDL is 60, this point load is 20, and this UVL is 30 kilonewton. Total 30 into 2 by 2 is 30. So 60 plus 20 plus 30, that will give 110 minus 76.67, which will give 33.33 kilonewton. So RA is 33.33 kilonewton. Now let us find out the shear force at various sections. Shear force immediately right of way is 33.33, because if you take a section, you will see only one load left of that. So shear force right of way plus 33 because it's upward. Now if you take left of B, 33.33 minus this part of UDL, that is 10 into 3, so minus 30. 33.33 minus 30, you will get 3.33. So 33.33 minus 10 into 3, it will give 3.33. Now if you take right of B, left of B you have 3.33, right of B is 3.33 minus 20, you will get minus 16.67. If you sum up from left side, 33.33 minus this part of UDL 30 minus 20, so it will give minus 16.67. Now you have to take left of C. Left of C, the summation will be 33.33. You can consider the total UDL, that will be minus 60 minus 20. 33.33 minus 60 minus 20. You will get minus 46.67. So left of C is minus 46.67. Now UVL also you have to consider either end, that is right of C and left of D. Right of C, when you take, you have to consider all these loads, but the part of UVL added will be negligibly small. Okay, right of C, the part of UVL is negligibly small, so you can take all these forces including this point load at C, that is the summation immediately right of C. So you will get 33.33 minus total UDL minus 60 minus 20, minus 60 minus 20 plus 76.67, which will give 30 kilonewton. So immediately right of C is 30 kilonewton. Next you have to take immediately left of D. Immediately left of D, when you take, the complete UVL will come. This is not a point load, this is only intensity. So when you are immediately left of D, this part is only infinitesimally small distance, and for that load part is 0. So when you take immediately left of D, complete UVL you should consider. So already we have the summation for right of C, that is shear force at right of C, 30 kilonewton. Immediately left of D, this UVL is 30 kilonewton. The resultant load will 30 kilonewton. So plus 30 minus 30 will get 0. So this summation, when you do it from the left side, all this summation, it's already there, minus this UVL, that will give 0. Shear force is 0. So summing up from left side, 33.33 minus 60 minus 20 plus 76.67 minus 30, that will give 0 as the shear force left of D. So that completes the calculation of shear force. Now you have to calculate the bending moment at various points. Again, bending moment at A and D is going to be 0. Now you have to calculate at B and C. Bending moment at A is 0. At B, there are two forces here producing moment at B. 33.33 into 3 clockwise moment. 10 into 3, this part of UDL is acting at a distance of 1.5, also producing negative moment, negative bending moment. So minus 10 into 3 into 1.5 or 3 by 2. So 33.33 into 3 clockwise moment, 10 into 3 into 1.5 minus 10 into 3 into 1.5 minus 10 into 3 resultant load into the distance 1.5, so will give 54.99 kilonewton meter as the bending moment at B. At C, when you consider, there are 3 loads producing bending moment at C. This 33.33 UDL, complete UDL, and this 20 kilonewton. So 33.33 into 6 meter, and UDL resultant will act here, that is center of 6 meter, that is 3 meter from C. So 60 kilonewton is the UDL, that is 10 into 6 into 3, the distance, that will produce a negative moment, and 20 will produce again anti-clockwise moment. writing the bending moment calculation. 33.33 into 6. Resultant load is acting here, 10 into 6. The distance is 3. And again another point load which is acting here, minus 20 into 3. That summation is minus 40.02. So bending moment at C is minus 40.02. And bending moment at D is to be 0. Now you can draw the shear force and bending moment diagram for this beam. Now we know the shear force immediately right of A and immediately left of B, 33.33 and 3.33. And we also know the variation of shear force. It is going to be linear under UDL. So 33.33 to 3.33. And when you look for the section BC, that is right of B, you have minus 16.67, and left of C you have minus 46.67. So minus 16.67 to minus 46.67. That variation you should show here. So you mark here BC, you should mark minus 16.67 and minus 46.67, and the variation under UDL is linear. And here you can join by straight line, because point load is decreasing that shear force. You have to only mark left of B and right of B. Left of B 3.33, right of B minus 16.67, so that you can mark. And then you have to join that left to right. The change what is happening is at that point, and that change is due to point load. Now again right of C we know 30 kilonewton, and left of D you know 0. So 30 to 0, and UVL shear force will vary parabolically, and under UVL shear force variation will be parabolic. It's not a straight line. UDL will make linear variation, whereas due to UVL shear force variation is parabolic. Now this parabolic curve can come either way, concave side down or concave side up. So here concave side is shown down, lower portion is concave side. That is because this zero intensity side is left side. If it's in the reverse direction, zero intensity side is right side. If the triangular load is like this, then you have to show concave side up. Okay, the variation you should show in the other way, because here the decrease in shear force, because the load part is less, the decrease is slow. Okay, decrease is slow. When it comes to the end D, there will be a rapid decrease. Slope will increase here. Here slope will be less, and here slope will increase. So here it's only gradual decrease, and here when it comes to the major intensity of load, there will be a more sudden decrease. So concave side should be down when triangle load zero intensity is left side. Okay. Otherwise, if a major intensity side is left side, then you should plot in the other way. There will be a rapid decrease initially, then later the slope will decrease, and there will be a gradual decrease. Now, to draw the bending moment diagram, we know bending moment at A is 0, and bending moment at B we have calculated 54.99 bending moment at B, and here between A and B there is no peak for bending moment, so there will be a variation, parabolic variation, because here UDL is acting. The bending moment variation is going to be parabolic, and it's going to increase till 54.99. There is no peak, so it is increasing to 54.99. And next, for section BC also UDL is acting, so it's going to be a parabolic variation, and we got the bending moment at C as minus 40.02. So you mark this 40.02 at C, and from B you have to show parabolic variation. Once again, there is no change of sign for the shear force, so no peak between B and C. So bending moment has to gradually go down. It has to go down till minus 40.02. So there is no peak here. So this is going to be the peak in that region, 54.99. So at C bending moment is minus 40.02 and at D it is 0 and the variation is cubic. So this variation is cubic variation. The bending moment variation is a cubic variation, and once again the concave side should be down. So always for bending moment curve the concave side should be drawn down, irrespective of whether it's a parabolic variation or cubic variation. The concave side should be down while plotting the bending moment diagram. But only in shear force diagram, when UVL comes, you can get concave side down or concave side up, that depending on where zero intensity side is or lower intensity side is coming. So here zero intensity side is left side. Wherever zero intensity is left side, from there the decrease will be gradual, and maximum intensity side the decrease will be rapid, and in that case concave side will come down. Now there is a point of contraflexure that is coming in the section BC. You should write down the bending moment equation for this section and equal to 0 to get the point of contraflexure. So you have to write down the bending moment equation for the section BC and equal to 0. So let us take a section in the portion BC at a distance x from left end. Now you can write down the bending moment equation. So this force is producing a clockwise moment, 33.33 x moment produced by this, and this UDL part, UDL 10 kilonewton per meter. For x meter the load is 10x, and it will act at the center of x. So this load is producing negative moment with respect to this section. So minus 10x into the distance is x by 2. So you get minus 10x square by 2. The 10x is the load. It acts at a distance of x by 2. So minus 10x square by 2. That is the moment produced by UDL. That is the bending moment produced by UDL with respect to this section. Now this 20 kilonewton will produce a anti-clockwise moment with respect to this section. So 20 into the distance. So you should subtract this distance 3 meter. So x minus 3, that will give this distance. So minus 20 into x minus 3, that you can equal to 0, because bending moment is 0 somewhere in the section BC and we need to find out that point. So you can reduce this 33.33x minus 5x square minus 20x plus 60 is equal to 0, or minus 5x square. Here these two terms result in this plus 13.33x plus 60 is equal to 0. Dividing by minus 5, you get x square minus 2.667, x minus 12 is equal to 0. Solving this quadratic equation using the formula, root is given by minus b plus or minus root of b square minus 4ac divided by 2a, where a is 1, b is minus 2.667 and c is minus 12. Solving this, you will get x as 5.05 meter. Since it is a quadratic equation, you will get one more value which is negative in this case, or the values which are irrelevant or not coming in this section can be neglected. So if you are getting say 1.5, that is not coming in the section BC and you should neglect it. So the values which are coming in that section has to be accepted as a solution. So x is 5.05. It is in the section BC. So that value has to be taken. In this case, its other values negative. So you can neglect it. Even if you are getting a positive value, you should check whether that value is coming in the section and then take it. So in this case, there is only one point of contraflexure. So that is 5.05 meter away, this point. So there is only one point where bending moment is coming to 0. So that point is 5.05 meter away from the left end. So we got the point of contraflexion. So we have completed the shear force diagram, bending moment diagram, and mark the peak bending moment also. We got the peak bending moment as 54.99 and maximum shear force is 46.67. This part is negative, so I not marked it here, but it's negative. But even though it's negative, that numerical value you should take, whether it's a bending moment or shear force. Sign should not be taken in considering the maximum shear force or bending moment. So maximum shear force is 46.67 and maximum bending moment is 54.99 and point of contraflexor is 5.05 from left end. That's all for today. Thank you for watching.